Welcome to this explainer. I am incredibly excited to take you on a rigorous, university-level deep dive into the precise hardware architecture that powers modern industrial automation. We're not just skimming the surface today. We're looking at the exact physical and logical structures that keep factories running flawlessly, around the clock. This educational material is prepared by Dr. Nima Mahvian. So here's our roadmap for today's masterclass. We'll be covering system architecture, hardware addressing, power supply basics, diagnostics and faults, and finally, backup and redundancy. Let's get right to it.
Section 1, System Architecture Overview, the macroscopic view of the S7.
Here's the complete S7 hardware architecture, fully assembled right on the rack. It's a lot like a giant puzzle, where every single piece is absolutely crucial. Notice the seamless integration of distinct systems here. You've got power supply modules routing energy right alongside memory maps and system addressing protocols, all smoothly locking into that physical backplane. Everything has an exact place, forming this highly organized, incredibly robust industrial brain.
Section 2, Hardware Addressing Rules, Mapping Code to Physical Geography.
Now, this illustrates a really crucial distinction we have to make in the S7 ecosystem, and that's logical versus geographical addressing. On the left, you've got logical addressing. That's your user-defined code freely assigned in your software. But look closely, there is a strict ceiling. We're talking a rigid 4 kilobyte capacity constraint for inputs and outputs depending on your CPU. Contrast that with geographical addressing over on the right. This isn't up to the programmer's preference. It is based strictly on the hardware's fixed physical position in the rack and its slot number.
So, the real kicker is how different modules actually consume this address space. Take a look at the top here. Digital channels use bit and byte addressing, so a standard 16-channel digital module consumes exactly 2 bytes. Now compare that to the analog channels below. Analog requires word addressing, meaning it utilizes 2 bytes per individual channel. That is a massive difference in how your memory real estate gets allocated.
Because of those differences, the system relies on standard, default addressing formulas when you plug these modules into a rack without any custom configurations. As a precise rule of thumb, for digital modules, the starting address is 4 times the slot number, -1. But for analog modules, the formula shifts pretty dramatically. It's 512 plus 64 times the slot number, -1.
Okay, let's walk through the applied math step by step. Looking at example 1 on the right, if we have a 16-channel digital module sitting in slot 12, our formula is 4 times 12 minus 1. That equals 44, right? So it yields bytes 44 and 45. Now check out example 2 on the left. An analog module in slot 6 uses our other formula, 512 plus 64 times 6 minus 1. Run the numbers, and that mathematically outputs a starting address of exactly 832.
Section 3, Power Supply Fundamentals, the lifeline of the S7 architecture.
Tracing the energy flow across the blueprint, you'll want to notice path A. This is your internal operating voltage flowing directly across the backplane to power the modules. Then we have path B, and that handles the external load current via the front connector for things like sensors and actuators. What I really want to explicitly highlight here is the S7400 architecture rule on the right. The power supply generates both 24 volts DC and 5 volts DC directly for the backplane. It literally handles both lifelines simultaneously.
Here, we can review the precise specs for the PS307 and 305 modules. You can easily see the input voltages, frequencies, and varying output currents, ranging from 2 amps all the way up to 10 amps. But please, pay heavy attention to the engineering note right down at the bottom. It explicitly states that all 24-volt DC outputs are short-circuit protected and, this is huge, they can be wired in parallel for increased capacity. That is an absolute game-changer for scalable designs.
All right, let's guide your eye right across the actual physical hardware of the S7300 front panel. Up top at label 1, we have the 24-volt DC indicator LED showing output voltage is present. Right below that, label 2, is your voltage selector switch and on-off toggle. Labels 3 and 4 show your input and output terminals, and you'll notice multiple terminals are provided to facilitate that parallel wiring we were just talking about. And finally, right at the bottom at label 5, there's a mechanical strain relief mechanism. That's just there to ensure those connected cables stay completely secure under intense industrial vibrations. Section 4, Diagnostics and Fault Protocols, Protecting Against Catastrophic Failure.
Look really closely at the cause and effect diagnostic matrix. If you get a short circuit that's on the third line, the output voltage instantly drops to 0. But the beauty is, the module automatically recovers to normal operation the second the short is cleared. However, contrast that with mains overvoltage right below it. If you hit the system with overvoltage, there is a very high risk of permanent module destruction. Basically, the system can save itself from a short, but it cannot always survive a massive voltage spike from the grid. Know why?
And that perfectly brings us to the advanced protection built into the S7 400 ecosystem. This unit generates dual outputs, 5-volt and 24-volt DC, and they both share a common ground connection. But pay very close attention to the protection logic box highlighted in red. It enforces extremely strict shutdown protocols. If a fault occurs on either output, the entire power supply unit shuts down completely. Why? Well, to protect that highly sensitive backplane from cascading electrical damage. It's a true lifesaver.
Now let's examine the physical architecture of the S7-400 front panel, which is exactly where these faults are communicated to you. Notice the exact locations here. You've got the upper diagnostic array packed with LEDs right at the top. Moving down, you'll find the control interface with the fault reset button, and lower still, you actually have dual battery backup compartments built right into the power supply fascia itself. Let's decode that front panel interface meticulously, because every single LED signifies a very specific state. The red NTF LED, that means an internal fault in the module. The red BAF LED triggers if the backplane bus battery voltage dips too low. Now on the right side, under switch controls, we have a vital control button, the FMR, or Fault Message Reset push button. So once a fault is physically corrected out there in the real world, you absolutely must press this button to acknowledge and reset the fault indicators.
Let's dissect the overload protocols now, and I really want to slow down here to highlight the critical defect state rule shown in the red box at the bottom. Check this out. If the 5-volt DC supply fails for more than 300 milliseconds, literally just a fraction of a second, the CPU is violently forced into a complete stop, known as the defect state. Recovery from this is not automatic. It requires a manual FMR reset and a full CPU restart, which, as you know, in a factory setting, means an absolute production halt.
Section 5. Backup and redundancy systems, ensuring zero downtime operations.
To prevent massive data loss during outages, the S7 400 uses 1 or 2 AA lithium batteries to fiercely protect the RAM and real-time clock. If 2 are installed, the second seamlessly takes over the moment the first one drains. Look at the calculation formula provided right here. So if we take an applied example of a CPU and modules requiring 175 microamps total, and we use a standard 1.9 amp-hour battery, we just multiply the battery capacity by a constant of 0.63, then divide by the total draw. This math gives us exactly 6,840 hours of backup coverage. That's over 280 days of memory protection. Pretty incredible.
But for continuous active operation, we rely on a high-availability, redundant architecture. By installing 2 power modules in the exact same rack, they actually share the load during normal operation. Now, if one module experiences a fault or a power loss, boom, there's a seamless, hot-swappable switchover. The surviving module instantaneously assumes 100% of the load without interrupting system operation for even a millisecond. And as we wrap up this explainer today, I want to leave you with this final provocative thought. When you look at the intricate math, the stringent protection logic, and the millisecond tolerances we've just covered, is strict adherence to these exact hardware engineering constraints the only thing truly standing between automation success and total global supply chain collapse? Something to think about. Thanks for joining me on this deep dive.